Here is a question that I'd like you to keep in mind as we go through the contents of this video. Let's say that we wish to run a multiple regression to explain academic performance as measured by GPA or the grade point average using three variables: IQ, gender, and income. We would like to do so for 1,000 students. How many elements will each feature vector have? Let's now turn our attention from theory to practice. Let's start building linear regression models using TensorFlow. Here is an approach, an outline of our line of attack. What we are going to do is start by getting a baseline implementation which does not rely on TensorFlow. This will just be regular Python code. This is so that we know what we are shooting for. We then move to TensorFlow, where we start by defining the computation graph. In the case of linear regression, all that we need is a really simple neural network of just one neuron with an affine transformation. We don't even need an activation function in here. The next step in TensorFlow is to specify the cost function. Here, the cost function will consist of the mean square error. This is our way of quantifying the goodness of fit. Given a set of points, we would like to minimize the cost, and that cost is the mean square error. Any minimization requires an optimizer, and in particular, TensorFlow relies on something known as gradient descent optimization, which we shall discuss in some detail. This optimizer object needs to be instantiated and given the cost function as well as the objective to minimize it. Once that's done, it will know that it ought to minimize the cost to improve the goodness of fit. Once we've defined the cost function and the optimizer, we actually carry out the training process. This is done by invoking the optimizer, but that optimizer goes off and does its thing under TensorFlow's framework. We don't actually need to carry out the optimization ourselves. Remember that the optimizer is trying to get the best values of the variables in our TensorFlow computation graph. That process of updating those values, those variable values, will be carried out for us. We will need to tell the optimizer what subset of the training data it ought to use and how many steps it ought to take. These refer to the batch size and the number of epochs. We will return to these later. Once the training process is done, the values of the variables w and b will be frozen. This will give us a converged and fully trained model that we can now use for new test data. Let's start with the baseline implementation. This does not require TensorFlow. The idea here is for us to know what we are shooting for. In this example, we will start by implementing simple regression. This has just one cause or independent variable and one effect or dependent variable. So we have one x variable and one y variable. Let's go ahead and very quickly see how this could be implemented without using TensorFlow, i.e. just making use of regular regression facilities available in Python. It turns out that there are a whole bunch of libraries we can rely on. Pandas is one important one. This provides an R-like abstraction for data called data frames. Another useful library is NumPy, which has a whole bunch of linear algebra functionality, stats models, which has specific statistical techniques and a toolkit for logistic and linear regression, and lastly matplotlib, which helps with plotting. Under the hood, this makes use of some powerful MATLAB functionality. Let's very quickly discuss some implementation notes. These are little details which are likely to come in handy when we are actually implementing regression in Python. Remember how negative indices in Python are interpreted? This is different than, say, in R. Basically, negative indices are backward indices. These count from the end of a container. So just as there are forward indices which start from 0 and go up to n minus 1, there are corresponding backward indices which can be used to access the same data using the indices minus 1 through minus n. Linear regression should never be carried out on trending data. This is because of the underlying statistics, and as a result, we often need to convert prices into returns before we can perform linear regression. Pandas data frames allow the conversion of prices to returns using the percent changes method in just one step. But if for some reason you are not able to make use of this method, you can achieve the same result using negative indices and a little bit of arithmetic jugglery as you see on screen now. Let's also understand the data representation that's typically used for machine learning based approaches to regression. This is in contrast to the coordinate geometry approach to regression. In the coordinate geometry based approach, the corpus consists of points represented as x and y coordinates. If we have just two variables, one explanatory variable and one dependent variable, we have just two dimensions in our points. We would pass all of these points into our regression algorithm, which is a geometric algorithm which would find the best regression line. This is not the typical machine learning based approach. In the machine learning based approach, we treat all of the x variables as features. And that means that all of those x variables together need to be represented using a set of feature vectors. These are then associated with a set of labels, which are the y values. This distinction between the feature vectors and the labels is a characteristic of machine learning based approaches to regression. This is how we would carry out a regression using NumPy, for instance. And in doing so, it's very likely that you'll find yourself using a function called reshape. Given a list with n elements, invoking reshape with the arguments -1 and 1 will give us a list of lists. Every list in this output is going to consist of just one item. This is an operation that we need to perform very often while working with NumPy. A reshape -1, 1 has the effect of taking one list and giving us back a list of lists. This helps to go from the coordinate geometry form of the x variables to the feature vector form, which we tend to use in machine learning applications. It's also important to understand the difference between simple and multiple regression. Simple regression involves just one x variable and one y variable. Simple regression is very easy to visualize in a two-dimensional plane because we have one cause and one effect. We could easily generalize this to increase the number of independent variables to more than one. If we have multiple causes for one effect, that is called multiple regression. Multiple regression is hard to visualize. It's still okay, it's still reasonably easy to do if we have two explanatory variables, because then we can represent this with a three-dimensional diagram. But as the number of x variables increases beyond 2, it is impossible to visualize easily because the x points are now going to be in an n-dimensional hyperplane. But this difficulty in visualization does not translate to any difficulty at all in the implementation. All of the procedures and virtually all of the implementations of simple regression can be trivially extended to deal with multiple regression instead. Let's now turn back to the question we posed at the start of this video. In a linear regression process, each one of the explanatory variables is going to contribute one value to the feature vector. So in this example, if our multiple regression has three explanatory variables, those are IQ, gender, and income, then each feature vector is going to consist of 3 points, one each for the IQ, gender, and income for a particular student. Note that a feature vector is specified per student, and so we will have 1000 feature vectors. Each of those 1000 feature vectors will have 3 elements.